Okay, thank you very much. My name is Paolo Comaron from UCL in London. And first of all, thank you very much to the organizers for have given me the possibility to be here and to talk today about the emergence of two-dimensional quantum turbulence in Polariton superfluids. So all the results I'm going to show today has been made in collaboration with the experimental group of Daniele Sanvito in CNR Nanotech in Lecce. This is a brief outline of my talk. I will try to give you a first introduction about what are exciton polaritons and why we call them superfluids of light. I will then show you some numerical results of our investigation of polariton turbulent flows. And finally, I will discuss the observation of inertial regimes in polariton fluids. So what are microcavity polaritons? Well, they are quasi-particles, which are the results from the strong coupling between cavity photons and quantum well excitons. I'm not going to give you much technical details, but I would like to tell you that these are quasi-particles that are bosons, so they can undergo Bose-Einstein condensation. From the excitonic part, they acquire interactions. From the photonic part, they acquire a very light effective mass, but at the same time, they also have a very short lifetime. So that's why we need to talk about two-dimensional non-equilibrium Bose-Einstein condensation, because there is always a competition between the time scale of the system which is needed to thermalize and the lifetime of the quasi-particle. So in order to reach a steady state, we actually need to continuously pump into the system to overcome the losses of the optical cavity. So how do we model the dynamics of such a system? Well, we can use the so-called driven dissipative stochastic Ross-Pitayevsky equation. So it's a kind of a sort of link to the previous talk. This is a GPE-like equation. I'm sure that you already recognize some GPE terms, like the kinetic term, the interaction terms. But in order to account for the pump and the losses, we also introduce some extra terms here. And we also move beyond mean field by using the truncated Wigner approximation and adding this white Gaussian noise that simulate quantum fluctuations. So among the major experimental achievements, of course, we find the first observation of polariton long-range order, which has been done in 2006. Then superfluidity has been measured by Jacqueline's block group in CNRS in Paris in 2009. The last 10 years, the polaritonic community shifted towards the investigation of the kind of the phase transitions these systems undergo and try to link it to the phase ordering physics. But it's of course true that there are still very many open questions about the turbulent behavior that these systems can actually exhibit. So thanks to the seminal works by Onset, Krajknan and Kolmogorov, within the conservative case, of course, we can draw like a simplified picture of the thermodynamics of a two-dimensional confined condensate. If we lower down the temperature, if we take, for instance, an atomic BC, we know that we can move from a disordered configuration, where there is a population of many vortices, to an ordered one, where vortex and anti-vortex pair are linked together, and this is the famous BKT phase transition. But what happens when we push more energy into the system? Well, the system needs to find a way to reorganize this energy and to push it to in a different way. The way that this system transforms this energy is to push it towards the motion of large scales structures of vortices that we call Onset vortices. This is indeed an non-equilibrium, like a steady state picture, but one can reach this steady state through dynamics, and of course we talk about inverse energy cascade. If one computes the energy spectra, there is a transport of energy from large k to small k with a power law that has an exponent which is the famous Kolmogorov exponent. And this physics has been investigated already a few years ago within the atomic BC framework, both experimentally and theoretically. These are two references if you're interested. But how can we discuss this picture in exciton polaritons? Of course, we have dissipation that destroy completely this picture. So, as I said before, the last 10 years, really the community pushed to solve the left part of this phase diagrams, to try to understand what are the new physics about the non-equilibrium phase transition. There are some references here, but also trying to solve relaxation dynamics of the system and understanding if there are new vortex configuration due to this driven dissipative nature. What about the right side? Of course, there are some preliminary results, but nowadays we are still not, there is not convincing proof that we could have on-circle clustering and observation of inverse energy cascade in superfluids of light. So we ask ourselves, is it possible? Is this physics observable? And if so, what are the mechanisms that drive these physics and the optimal condition for the experimental observation? So we decide to tackle this problem first numerically. So we look at the relaxation dynamics in a finite decaying system. We focus first in the conservative case. We have our stochastic gross beta escape for polaritons. We start from the easiest of the configuration, which is a confined condensate with a flat density. We imprint the same number of vortex and antivortices, 40 and 40. And then, if we start the dynamics, we will see that there will be a large number of events of annihilation of vortices and antivortices that will decrease the total number of vortices. We can quantify the clusterization of the system by computing the clustering correlation function, which takes the value of 1 in case we have two massive vortices, cluster of vortices, the values of -1 instead if we have all vortex pairs. And of course, looking at the dynamics, we can see that the clustering correlation function increases as a function of time. And if we look at the phase, we can see the appearance of small clusters of vortices with the same sign. So let's compare the conservative with the dissipative case. Of course, if we dress the condensate with the polariton with a short lifetime, we will see the density decrease, and of course, okay, perfect. And we will see, of course, the number of the healing length of the vortices will grow as a function of time. So the correlation length will grow initially, but then eventually, if we wait enough, will be completely killed by the dissipation. So with dissipation, the vortex motion is damped, and the formation of these on-circle clusters is compromised. Still, we are happy because we can see that initially, we can have a transient where we can see the onset of this clustering. So then the question is to try to find the optimal condition that maximize this clustering before the dissipation destroys completely the picture. So we answer to this question solving numerically different initial vortex density. So we fix the initial number of vortices, and we change the drop size so we can kind of tune the initial intervortex length. We look at the conservative case, the dissipative case. So already at the conservative case, we can see that a more dense and therefore more interacting vortex gas enhance the onset of clustering of vortices. And this makes sense because, of course, the annihilation processes takes place at length which are as small as the healing length. But it's interesting to note that if we have a too dense vortex cloud, there is a case where the correlation function initially decreases and then eventually increases. So we look at the wave function and we find that this is due to the frequent annihilation of vortex-antivortex pairs that creates much sound and will eventually hamper this clustering. So the clustering is kind of quenched. If we go to the dissipative case, well, we have this growing healing length, so the picture is definitely not trivial. We need numerics, we compute different curves, and of course we find that there exists an optimal curve for which clustering processes are maximized, and we can extract this curve numerically. So what we learned from this numerical study is that the intervortex length is crucial for clustering. If we have a cloud of vortices, and this is to dilute, they're not really much interacting, so the clustering, it's very slow. So we need to bring them back together. But we have to be careful not exaggerate, because if they are too much dense, then plenty of annihilation will take place, much sound will be produced, and the clustering will be slowing down. So we have a maximum on the curve. So quick summary, clustering is governed by competition of different factors. We have dissipation, annihilation, interactions, and we are happy because we found that clustering in this dissipative system can actually be observed within realistic time scales. But most importantly, we found the knob for tuning clustering, which is the intervortex distance. So after our numerical study, we go to the lab. So these results I'm going to present now have been taken at the CNR Institute in Lecce. So excitonic, Polariton experimentalists are able to trap the Polariton fluid by creating some trapping by means of CW lasers. After many attempts to find a particular good way to imprint vortices and create like a Polariton fluid, we find that the optimal one was splashing this Polariton fluid inside the confining potential, similarly to pouring some red wine inside the glass. So as we can see here, we initially inject the Polariton fluid, and then if we follow in time, here there is a movie, if you can see it, we can see that the Polariton fluid will expand, hit the barrier, and go back, gather at the center of the trap, and here there will be much chaotic turbulence, vortices, and sound will interact together. So in Polaritons, the laser blue shift from the bottom of the trap is actually equivalent to the initial kinetic energy that we inject into the system. So, of course, if we have a high detuning, we will expect to end up with a faster velocity of expansion and a higher vortex density. But then this is very nice, because we found our control parameter for the clustering. We can use the detuning to imprint more density of vortices to decrease the intervortex length. Okay, so then we, thanks to very sophisticated interferometric techniques, experimentalists can actually, from the leaking light of the cavity, they can extract psi entirely, and the phase, so we can analyze the phase, track the number of vortices, look at the circulation, and then we take two different data sets, one at low detuning and the other at high detuning, which are plotted here. If we count the number of vortices as a function of time, and if we compare the high detuning, which is the red, with the low detuning, which is the blue, we can see that, as expected, we have a faster dynamics and a higher number of vortices for the high detuning case. So we push the analysis forward and we classify our vortex cloud. We're inspired by this work, and we distinguish between free vortices, dipoles, and clusters. If we look at the low detuning case, nothing really exciting happens. If we look at these different three species as a function of time, you can see that they are pretty constant in time. But if we move to the high detuning case, we can see that for a particular transient, we have that the number of dipoles decreases at the expenses of the number of clusters. Okay, then what we move forward, we apply the Helmholtz decomposition to the velocity field. We extract the compressible, incompressible parts of the velocity that are associated respectively with the sound component and the vortex component, so we can compute the incompressible, compressible kinetic energy spectra. And finally, we also calculate the clustering correlation function. We take all these observables and we gather all together. So we have correlation function on the top. We have the ratio between compressible energy in the middle, and these three different classes of vortices on the bottom. And we can see that indeed at the beginning there is an expansion transient, but eventually between 40 and 80 picoseconds, we can see that all these different quantities suggest that there is a heating of vortex gas that wants to approach an Onset vortex. Because we have, for instance, for the high detuning, we have that the correlation function increases, the compressible energy transforms in incompressible energy, and we have this number of clusters that increases as well. So finally, and this is the last slide I would like to show you, we compute the incompressible energy spectra from the low detuning and high detuning case. For the low detuning case, nothing really is not really interesting, but in the high detuning case, of course, we can measure within a very short range of momenta a power law with an exponent which is compatible with the Kolmogorov exponent of the classic turbulence. We take our model, we simulate similar setup, and we find a very good agreement with the experiment. And with this, I think I would like to conclude. We investigate numerically, experimentally, turbulence in Polariton fluids. Numerically, we understood that the intervortex length is indeed crucial quantity for the clustering. Experimentally, we find that the tuning of the laser can be a good control parameter for the clustering. So our results show that there is a tendency to form the clusters. We find that there is some inertial range regimes that are very short, but they are there, that looks like compatible with standard classical turbulence. So I hope I kind of convinced you today that polaritons can actually be a good platform to investigate two-dimensional quantum turbulence. And this is the reference. Would like to thank all the organizers, especially the authors, and especially Michał Matuszewski, which was my former supervisor in Poland, but especially Ricardo, Dario, and Daniele that undertook the experiment. And with this, I would like to thank you very much.
I wonder if you ever plotted the number of point of vortices as a function of time. And
in the experiment, in the theory?
Both the experiment and the numerical simulation. How does the line, the vortex point decay with time?
So you mean the number of
yes.
vortex?
Yeah.
Yes. So let me go back. So I have to say that between the theory and the experiment, there is a discrepancy because, of course, the initial condition is different, but let's focus on the experiment. This is the number of vortices as a function of time. So
so the number of vortices increase with time?
In the low tuning case, it increases a little bit with time during the splashing, exactly. But in this is a good point. In the high detuning case, we have a pretty constant number of vortices. What happens is, of course, we have this splashing. We were waiting that the decay starts to decrease, but before this happens, we have that the dissipation destroy the pictures. We have to say that this is a very complicated turbulent flow in a sense that there is always generation of pairs of vortex and antivortices. So they annihilate and they create at the same time. So that's why we think that at this point the number of vortices is constant. Well, at some point they dissipate and they just drop to zero, so we just don't plot what is dissipating is the fluid, in the sense that the density decreases. And of course, in an ideal case, we go back to the numerical study and we see that a beautiful exponential decay of number of vortices. But this is not the case because, again, there is a generation which is due to either defects in the sample and into, I don't know, wave turbulence. So the situation is very much complicated and complex.
You see, the physical picture proposed by the Australia group is, the number of vortices decreases.
Absolutely
but
agree.
The kinetic
absolutely
energy
agree.
is
Yes.
Incompressible kinetic energy is more or less conserved.
Yes, yes,
so
yes.
energy per particle increases.
Yes.
But here, if your number of vortices does not change, I don't understand where the energy comes from.
Yeah, you're right. The fact is that there is not just the fact, let me go on the right. So initially we were also puzzled because we wanted to see the number of vortices to decrease. That's why we really had to take all these different observables and see all these different curves and try to interpret. But once we see that the compressible energy transformed to the compressible, that we have the growing correlation function, and that the number of clusters slightly increases, that will be that was sufficient for us to say that there is an onset of clustering.
It's a very short experiment range.
It's between 40 and 80 picoseconds. Yes. 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 So at the beginning we tried. Yeah.
So you're saying essentially there are a lot of compressible energy in the system, in the state.
There is loads of compressible energy in the
So
system.
compressible energy
Yes.
converts to
If
incompressible.
okay, so in Onset condensations, you would expect, I don't know, the Australian experiment, they go almost to 1. 1 is where you have two giant vortices. Here we are approaching 0. So we are not saying that we are in the ideal picture of the, but we are saying that there is a tendency, there is an onset of vortex clustering. It was really a fight. We spent loads of years to try to just get this initial transient, because it was a proof of concept that an initial, that the system tried to go towards that kind of physics.
Sorry, another question.
Yeah.
I think here you introduce this vortex spacing as a tuning parameter. But have you thought about the size of your trap?
Yes.
Because in the end, you see there are some certain number of state on the surface, and then certain number of state inside. You can consider how many vortices could escape from the boundary, and that mechanism essentially depends on the ratio of surface state to the interior state.
Okay.
So could that also affect the formation of uncycled vortices in your system?
I don't think we are. This is a very fine-tuning problem, let's say. I would say, because the I know that there is vortices that escape from the let's say from the trap, and that could heat the gas, of course. But in this case, again, the situation is so much complicated that we cannot really see vortices going. If you see again the movies, you can really see that there is generation of vortices and annihilation of vortices. It's very much complicated. What I can say is that initially we tried to really imprint the vortex cloud as we did at the beginning, as I show you in my numerics, okay, where we print same number of vortices. The problem with polaritons is that they have a very repulsive force due to the fact that the laser is usually top up. So what happens is that without confining, they will just escape. If you use the trapping potential, then the only way to excite vortices was to splash them. It was a very technical challenge.
One last question, perhaps?
Yeah, so you showed the energy spectra at the end that it has the -5, and -3. When does this spectra establish? Is it at the beginning? Is it during
This
the
is
clustering
in the
regime?
This is the integrated time. This is the time integrated spectra between 40 and 80 picoseconds.
40 and 80. And in the early expansion period, and
in the early, you can see that it's go a little bit flat. So it's kind of flat, and then at some point the shape it's established. Of course, here this is just a way to plot it. We divide by k to the -5. But I mean, -5/3 like that. So it's go a little bit flat, and then it stabilizes on the -5/3. We thought about this. We have seven points. I don't know if we can say it's a plateau. So we 1, 2, 3, 7. I mean, I don't think we. I mean, yeah, we thought about this, but claiming that this is a plateau, we were not really sure.
Okay, but you have a very clear K-3 law. Why?
Perhaps we
No, because well.
coffee, perhaps you can
The fact that we have the loaded tuning and just so the fact that this is not the minimum we can go. We just choose two different values of low and high the tuning. So thank you.